let's try again, is just the location of electrons, okay? That's what it's all about, is we're going to be learning about the electrons that are on the outside of the nucleus in the electron cloud and how much we have learned so far about how to determine where they're at. Because we know from Bohr's planetary model in our last unit where electrons rotate around the nucleus, so like for example, like perfectly around the nucleus, like you have all these electrons that are just perfectly going around it in this cute little orbit, like in a circle, doesn't really happen. In reality, they look a lot more like our cloud model down here, where they're kind of all over the place, but they do still stay in certain energy levels. So like they are going to stay in that basic location away from the nucleus, but they're not going to stay in that perfect orbit. They're going to bounce around and they move so fast, it's actually really hard to see them. All right, so let's begin. So the quantum mechanical model is the first blank. The quantum mechanical model is the model we currently use to describe what the atom looks like. So that's our current one, newest one. The quantum mechanical model of the atom was developed based on the work of an Austrian physicist named Erwin Schrödinger. In 1926, he developed a mathematical equation to describe the energy and the location of the electron. Okay, so that's what his goal was the energy and the location of where these electrons were at in the atom. This equation, called the Schrödinger's equation, has been extended to describe electrons in other atoms since the one he based off of his original mathematical equations are based on hydrogen. They have been extended to other atoms now as well. So like I said earlier, unlike Bohr's model, which had them going around in the perfect orbits around the nucleus, we now know with Schrödinger's model that it's more of concerned with the probability of finding an electron in a certain location. So it's basically, as we just know, it's a lot more complicated than the way Bohr made it look like, where they flow in that perfect pattern around the nucleus. In reality, they are all moving very, very rapidly in the same energy levels, but so fast, moving in a way that it's really hard to detect them. So we had to have these new mathematical equations trying to find where they were at, so we could try to discover later how they bond. So the Heisenberg's uncertainty principle states that it is impossible to precisely know the location as well as the velocity, which means speed, basically. So location and the velocity of an electron. Therefore, the model is portrayed as an electron cloud because it's very hard to determine their exact location if I'm also trying to determine their speed. If I'm looking for both, I really can't find both at the same time because they move so fast. So basically, by the time I find the location of an electron, it's going to have moved. So what it looks like when we actually look at microscopes that can zoom in to the furthest levels we have today, we still cannot clearly see the protons and the neutrons of the nucleus staying exactly still and the electrons staying still. Basically, the pictures that we take of atoms look like this fuzzy wuzzy cloud. That's why it's called the electron cloud, because they're moving so fast, it's almost like they're all over the place at once. Now, therefore, the model is portrayed as the electron cloud. By convention, a line is drawn for the surface of the atom at 90% probability. So basically, those mathematical calculations are supposed to get us to know where the electron is, its location, 90% probable. So it's 90% sure that we're there, that it's there, but again, they do move so fast that there still is that 10% error. All right, let's scroll down. So within this cloud, there are various energy levels. Okay, all right. There are various energy levels, regions around the nucleus where electrons are likely to exist. Energy levels in an atom are summarized, and these 4 parts are about to go through to summarize the energy levels of an atom. So again, when I say energy level, what I mean is if I had a nucleus here, okay, so here's our nucleus, I'm talking about how far away, like literally the distance away from the nucleus. So if I have electrons that are staying this far away at energy level 1, they can move all around in there, like all over the place, moving really, really fast, but they're going to stay within that energy level unless they're given extra energy that we'll talk about more when we get to life. And then we're going to have some electrons that get pushed out to this level, and they can go anywhere inside this level, all over these energy levels. I mean, all over this area in that energy level, but they're not going to move to any other level. They're not going to drop down. They're not going to drop up unless they are given more energy, which again, I said we've mentioned in life. And then you might have some electrons in this energy level. If it's a bigger atom, they might be further out. But basically, the bigger the atom is, the more protons and electrons it has, the more energy levels it's going to need to use. Because electrons cannot all take up the same place, because an electron is negatively charged. So when I get an electron next to another electron that is also negatively charged, they will repel each other. So I can only have so many electrons in the same energy level, so the same distance from the nucleus, before they're going to start bumping into each other and repel each other. So I can only have a couple per energy level. We're going to break that down, how many actually fits before they have to move further away from the nucleus. So from that, you might wonder, then why don't they just float away? Why aren't they just floating off into space? Why do they stay near the atom at all if they're repelling each other? Well, the reason being is because what is in the nucleus? So inside the nucleus, there are protons that are positively charged. So those electrons that are negatively charged are attracted to those positive protons, and that is why they stay. They're staying as close to the nucleus as they possibly can be because they're attracted to the positive protons, but they repel each other, the electron, because they're both negative, so they have to spread out. So it's like they get as close as they can, but as far away from each other as they can to help to stay together in the atom. All right, so now we're going to break down these 4 parts of energy levels that you will need to understand and be able to use. Okay, so our first part, part 1, the size and number of energy levels in an atom corresponds to the row, okay, to the period. To the period or the row. Remember, row means horizontal on the periodic table. So the period that the atom is in on the periodic table. So like for an example, if I draw a quick little periodic table here, it's probably going to be pretty terrible, but there you go. All right. So if I put my little energy levels, these numbers are on your periodic table. It says 1, 2, 3, 4, 5, 6, and 7. So when you look at your periodic table, copper is Cu, and it's right here. I did not a very good job lining it up. It should have lined up with 4, okay? So it's in the row 4, so it has 4 energy levels. Again, what that means, if I have a copper atom here, it has a nucleus, and it's gonna have some electrons at energy level 1, it's gonna have some electrons at energy level 2, it's gonna have some electrons at energy level 3, and it's gonna have to have some electrons all the way out there at energy level 4. The furthest out that electrons can get is energy level 7. They don't really get further than that, because any further than that, and they really can't feel the pull of the positive protons anymore, so then they would just float off into like empty space out and around. They wouldn't be attached to their atom anymore. Okay, so now silver. Silver is, let's see, it's right below Cu. So it's right below it. So it's in row 5. So it has 5 energy levels. So like silver would have 1 more energy level. It's to have electrons. It's a bigger atom. Its electrons would be further away from the nucleus. And then we have radium. Radium is all the way over here in the column 2, but in row 7. So it's one of our biggest atoms on the table. Not the biggest, but one of the biggest. And it has, my bad, scribbles, has 7 energy levels. So it has the 5, and I'd have to go all the way to a level 7 being the biggest that atom could be. Okay? Now we're going to scroll down to part 2. right? So part 2 tells us about not how many energy levels an atom has, but the shape that that atom will take. So the electron clouds don't all look like a round ball the way we tend to draw them. They actually come in some pretty intricate shapes. And we can see that when we do close-up images of atoms with the most precise microscopes that we have. They actually make these very odd shapes. So what they are, we've given them little letters to remember what they look like. So S, we're going to remember what it looks like because it's going to stand for a sphere. So if you are in a S-shaped electron cloud, the electrons are in that cloud, they do take on a circle, okay? So all their electrons are inside a circle, okay? So a circular shape or a sphere because it is 3D. And then if you're in a P shape, so a P-shaped orbital or a P subshell, P stands for peanut. Now, not really. These are names that people have made up to help you remember what they look like. So when I think of a peanut, I think of like that. Okay, so kind of like a figure 8 as well. Now, in the peanut, there are actually 3 versions that this can turn around the center. So this one would be a Y version. There'd be an X. That's a terrible peanut, sorry. Maybe a little better. And then we have the Z plane. So what I mean is if you can remember from geometry, like if I have the X and the Y plane, so like this peanut is literally on that X plane, this one would be up and down vertical, and the Z plane would be coming out like at you. So like more horizontal, taking the space around the nucleus. So in all these versions, the nucleus is in the middle. Okay, the nucleus is in the middle of those, and the electrons are anywhere inside this peanut shape, anywhere inside this peanut shape, anywhere inside this peanut shape. Okay, so they could be anywhere in there. Okay, and then we have the D shape. So for that one, I usually say that it looks like a double peanut. I know that's silly, but it's just a way to remember it. So a double peanut meaning I draw one peanut and then I draw another one. Okay, so that means if I have that nucleus in the center, the electrons could be anywhere in here, anywhere in here, anywhere in here, or anywhere in here. All of those places are available for that electron to go in. And for the for the D subshell, it actually has 5 versions that it could turn. So 5 versions, if I was imagining this in a 3D space, which will be easier when I show you pictures in a second, hopefully, 5 versions around it. I'm not going to draw all 5 versions because it gets really complicated to draw. But just imagine that if I took this shape and I turned it in different directions 3D wise, I could turn it 5 different ways. The last one, F, stands for fancy for me because it is so fancy looking and complicated to draw that I don't bother. Okay, it's very hard to draw all those, and F actually has 7 versions that it can turn around the nucleus. So I'm going to scroll down just so while we're on this topic and show you the pictures of all this. So this is later on our notes, but see we have pictures right here. So the S orbital looks like a sphere, and you can see that there. And then we get to the peanut orbital. Wow, I really need to erase. So erase, erase, erase. Okay. So for the peanut shell, remember I said it has 3 versions. So it has 3 ways you can turn it. And this is on the X plane, so going horizontal, Y plane up and down, and then Z plane coming out at you. All right. We scroll down and we see the D subshell, and it has 5 versions. So you see 5 different versions here. Now 4 of them look like that double peanut that I showed you. So it has 5 versions. Remember, it stands for a double peanut. So it looks like 1 peanut, 2 peanut, and 4 of them look like that. So they're just turning that shape different ways around the nucleus. But 1 of them makes this very weird shape, and you'll see that in the F subshell as well. So it's very complicated. I don't generally draw the D subshells. I don't require y'all to draw them because they just get more complicated to draw. And then lastly, we have F, which is fancy, because as you can see, it's pretty fancy. It has lots of orbitals. It takes any of those electrons could take any of these spaces around the nucleus. They could literally be anywhere in any of those 7 choices. Okay. I'm going to scroll back up to where we left off. Yeah, so right here. So we can break that down a little further. It says the number of subshells or sublevels in an energy level is equal to the number of energy levels it has. Okay, so in energy level 1, we already went over this. So like literally the first row on the periodic table, row number 1, has 1 subshell. They always match. So whatever row you're on, that's how many subshells it has. So the subshell to fill it is going to be just an S. It always starts with S's and then moves on to the P, D, and F shapes. So with one sublevel, it's only going to fill up an S shape. In energy level 2, so when I get to row 2 on the periodic table, they have 2 subshells. And the electrons could take the S shape in a sphere or the P shape in the peanut. Energy level 3 has 3 subshells. So if I'm on row 3 on the periodic table, they can take an S, a P, or a D shape. Energy level 4, I feel like you get the point by now, has 4 subshells. So I could have an S, a P, a D, or an F subshell. All those shapes would be available to the electrons that atom has. Energy level 5 has 5 subshells. So we got an S, a P, a D, an F. And then there are G's that we put this little asterisk by it because only the S, P, and D and F subshells will actually contain electrons, but basically they have this F available shape to those very big atoms that sometimes the electrons pop into. We don't really talk about those because that's kind of above our level of chemistry where we're at. So energy level of 6 would have 6 subshells, so it could have an S, a P, a D, an F, a G, or an H. And again, that H is going to get an asterisk, the G is going to get an asterisk, because in reality, the electrons don't really go there unless pushed up. Okay. Now, before I go over how many electrons are actually in there, I want to show you where these things are at on the periodic table. Now, if you were actually in class, we're going to add these labels to their periodic table. So if you have a periodic table, if you can print yours at home, it'd be a great idea to add this to your table so you wouldn't have to always pull this up. So if you're looking at this periodic table here, you see our energy levels, 1, 2, 3, 4, 5, 6, and 7, but they're now labeled with S, P, D, and F. So right here, this whole area here, all is labeled with S's. So this is always where we start and it's labeled with S's. So all the electrons found in this area are going to be in a sphere shape. And then what actually we hit next, because basically you just trace your finger. I'm going to go across and what I hit is still a 1S. So this is still a sphere shape. But then I go back to the beginning and I would hit a 2S, so sphere shape, and then I get to a 2P. So energy level 2, 2 distances away from the nucleus, and now we get to our P shape. So this entire block over here, if you find that the element is in this area, then it has P-shaped orbitals. If you find an element that's down in this block, well, they're going to have passed S's, they're going to have to have passed the P shapes, and then finally have gotten to a D-shaped orbital. So they're going to have S's already, they're going to have P's already, and now they're also going to have electrons in a D shape. If you have electrons way down here, I want to point out on your periodic table, technically these come from right here. They come from right there. So this is actually energy level 6 because it comes from right there, and energy level 7. It's just an extension. It's like a longer 6 and a longer 7. So if I find my element on this, though, this is where the F shape starts. So if you had an element here, that would mean that the electrons in that element took the shape of S's first, then P's, then they'd fill up the D shapes, and then they would start filling up the very fancy F shapes. So again, I realize that this sounds very complicated. The actual work that you will do with this is very simple. Hopefully it will make more sense tomorrow. I'm just trying to give you a little bit more background to work with, but all it means is electrons take different shapes away from the nucleus, and how far they are from the nucleus is determined based on what row they're on. So if you find an element on this row, that's how many energy levels away from the nucleus they are. They're 4 levels away. That's how they, so it's kind of telling you the size of the atom to some degree. All right, let's go back and finish what we had left. So part 3, below is the number of subshells, or is it orbitals? One moment. Below is the number of orbitals. So the number of orbitals in each subshell and the orientation of these orbitals. I've basically already told you this. It's just kind of reiterating it and giving you it in note form. So the S sublevel only has one orbital. And remember, the S is a sphere. So if I'm imagining the nucleus is in the middle of that and the electrons are in that shape of a sphere around the nucleus, there's only one way to turn a sphere around a nucleus. I can't get any other location around it. Like if I turn a ball around the center, like it's still taking up the exact same amount of space. So it only has one way to turn it, only has one orbital. So there's only one shape that those electrons can be in. If the element is found in the P block of the periodic table, then the peanut shape, so remember that peanut, I can turn the peanut in 3 different ways, and the electrons would actually be taking up a different spot, a different area outside of the nucleus if I turn that shape around, unlike a sphere. So like the sphere from the S, I can't turn it in any way to actually make it take up different amount of space. But the peanuts I can. So it has 3 orientations. For the D subshell, it has 5. For the F subshell, it has 7. So basically what you should be noticing is this is 1, this is 3, this is 5, this is 7. So like a way to help you remember is on the periodic table that should be labeled, or you have this in your notes, that I'll post it, SPDF, they each go up by 2. So it started with 1, goes up by 2, goes up by 2, goes up by 2. And that's how many ways you could turn it. That's how many shapes it could possibly take more than the original. All right. Scrolling down to part 4. So each orbital can only hold 2 electrons, and that they must be spinning in opposite directions. Okay, so this is where I'm getting to the point of telling you, well, how do you know how many electrons can actually fit in there, and where are they all going to go in the shapes? Well, each shape I just talked about, so one sphere can hold 2 electrons. If I have a peanut, this peanut can hold 2, but remember the peanut subshell, or the P subshells, have 3 ways I can turn it. So this one could hold 2, and this one could also hold 2. So really, the P subshell can hold 6 total electrons. But because the S subshell can only be turned in one way, it can only hold 2 electrons total before other electrons that atom has would have to move to a higher energy level or to a different shape outside of it. So overall, what do the 4 parts tell us? So the first part told us the number of energy levels in an atom, and the kind of the distance away from the nucleus it would be. The second part told us the shape. So if I look at the periodic table and I have those blocked out shapes, I know from where the element is at if it's going to have an S, a P, or a D shape to the electron cloud. The next one, how many of those shapes? So like how many orbitals? Like this has 3 and this one has 1. So how many orbitals or shapes will those electrons take? And then lastly, the number of electrons it can hold. All right. Now I'm going to help you. The next little section is me showing you how to do your assignment here in just a second. So you'll have similar questions to this on your assignment, and then we are done with notes. Okay, so in the sublevel S, there's only one way to turn it. Remember, there's only one way to turn a sphere around a nucleus. And for every orbital, every orbital can only hold 2 electrons. So if there's only one, then the total amount that an s subshell can hold is 2 electrons. And the p sublevel, it has 3 ways that I can turn that peanut shape around the nucleus and it take a different actual space around it. So since it has 3 and there's 2 in each one, it'd be 2, 4, and 6, so it can hold 6 electrons before we'd have to move up to a different level. The D block has 5 ways that I can turn that double peanut shape. So if I have 2, 4, 6, 8, 10, so 2 in each one, that means that it can hold 10 electrons. And then lastly, the F block has 7 orbitals, so 7 ways I can turn that fancy shape around, and in each of those orbitals, they each can hold 2 each, so 7 times 2 is 14 electrons. So that's how the breakdown goes with our sublevel and how many electrons it can hold. Okay. For energy level 1, so if I'm thinking, this is thinking about the periodic table again. So if I have our little mock periodic table, and that level 1, if I go across to level 1, that's just hydrogen and helium, all I'm going to be hitting is one sublevel. The name of that sublevel is a 1s, and if I only have 1 in it, then it can only hold 2 electrons, okay? So I want to show you this next one for number 2. So like, what am I going to be touching when I scroll to 2? I'm going to go look at the periodic table. So energy level 2, if I'm starting here, the whole energy level 2 has an S shape. Remember, there's 2 electrons in an S shape, so it can hold 2 electrons. I keep going, I hit the P block, and I hit just 2p. Remember, in the P block, it can hold 6 electrons. So if I could hold 2 in my S shell and 6 in my P shell, both of them being energy level 2, both of them being 2 degrees away from the nucleus, 6 plus 2 is 8. So that's how many electrons total that it can hold in the second energy level. So in that row number 2, any element that is in the second row on the periodic table cannot be more than 8 electrons in the second row. So I have, let me scroll up because now I forgot what it's called. So number of sublevels, 2, because that just goes with a row. It's going to hold a 1. Nope, not a 1. We crossed a 2s and a 2p. So remember, there's 6 in p's and there's 2 electrons in s's. So that's 8 electrons total for the second energy level. In the third energy level, there's going to be 3. Okay, so there's going to be 3 sublevels. It always matches those numbers, is how many sublevels it has. It crosses a 3s. Then it will cross a 3p. And then down below it, eventually hits a 3d. Now, 2 electrons in each one, so this one holds 2 electrons. P has 3 orbitals, so 3 times 2 is it holds 6. D has 5 orbitals, so 5 times 2 is 10, and then I add all those up. So 10 plus 6 is 16, 17, 18. So energy level 3 can hold 18 electrons. And the fourth energy level is going to have 4 sublevels. It's going to be a 4s, and then it's going to be a 4p, and then a 4d, and then a 4f. All of those you can find on your periodic table labeled, especially in the one that I will post and those notes that I keep showing you. So there are 2 electrons in s's, 6 total in p's, 10 total in d's, and 14 total in f. So if I add up those, so that would be 24, and then I have 30, and then I have 32. So in energy level 4, it can hold a total of 32 electrons. Now, if your element was below energy level 4, it was the very last element in row 4, which is krypton, then I should be able to add up all of these that it had before. So 2 plus 8 is 10. That'd be 20, 28. You scroll down, so that'd be 28, 38, 48, 58, 60. So is krypton number 60? So that is incorrect. I thought you could add them up and get the same number in the periodic table, but nope, disregard. All right, scrolling down, and you're going to have some of these questions on your periodic table and your assignment today as well. So hopefully this will be helpful to go over how to answer them. So put an X or sublevels below which do not exist. So if I scroll down to my periodic table and look for 3p and 1d, which one of those does not exist? 3p and 1d. Okay, so 3p exists right there. But then does 1d exist? When I start in the D block, it already starts at an energy level 3, meaning we don't even have electrons in a double peanut shape, in a D shape, until they are 3 levels away from the nucleus. They're not going to take that weird shape until they get at least 3 levels away from the nucleus. So 1d does not exist, but 3p does. So if I scroll back up to our practice, 3p exists, 1d does not. Give the number of orbitals present in the following sublevels. So for this one, the number of orbitals present is always based on the row it's in. So this is the row it's in. It's in row 5. So it has 5 orbitals online. That's just because of D. So D has 5 orbitals. P has 3. So when we're talking about orbitals, we're talking about how many ways I can turn the shape. So remember in P, I can turn it this way. I can turn it this way. I can turn it this way. In D, I can turn it 5 ways. So that's just straight from your notes. Give the number of electrons present in the following sublevels. So again, S can only be turned one way. There's only one way to turn a sphere. Each time you have a new shape, it can hold 2 electrons each. So it can only hold 2 electrons. P, as I said right up there, has 3 ways to turn it, 2 electrons in each one of those. So I would get 6 total, 2, 4, 6. Electrons is how many total could be held in a 4p shell. Okay. So that is where we're going to stop. And I will post these notes so you have that periodic table to look at, because I'll be having the kids in person actually label the SPD block on their notes. So if you have a periodic table, it'd be great to add that to it. But if you cannot, I will post these notes